So the topic of today's lecture and the next few lectures is basically different ways of doing what's called linear classification, right? So today's lecture is really linear models for classification. And if you remember last lecture, we were talking about linear models for regression, right? So regression is basically predicting a certain numerical value. Classification is sorting things into one class or another. And so much of machine learning has to do with this kind of like classification of objects into boxes that we're going to spend some time on that. So again, let me just say what I said. So regression is predicting a continuous real number. Classification is assignment into one of a discrete set of classes, right? So these classes could be like, cats versus dogs, or, qualifies for a mortgage or doesn't qualify for a mortgage, or engineering student, science student, arts student, humanities student, right? So basically, the key thing we're going to do today is find a function that assigns an observation to a class, right? So we want a function y of x that assigns an observation to a class, right? So the classes, for the sake of argument, let's just suppose we have k classes, right? 1 through k. So such a function that goes from observation space to one of this labeled set of classes is called a discriminant. Okay, and so today we're going to talk about what are called linear discriminants, where this decision basically is like a linear combination of the input features, maybe plus a extra constant. Okay, so that's what we're going to talk about today. Today we're going to talk about what are called linear discriminants, which is a fancy word for a simple concept. It's just saying that my function is, again, you've kind of seen this before, where I have a weight vector and I have a bias. Okay, and so you're going to say, well, this looks exactly like what we talked about for regression. Why is this different from regression? So the difference is how I use this linear function, right? So let's suppose that we have two classes, right? So basically, example with two classes. We can say that if this function is greater than 0, then I choose class 1. Otherwise, I choose class 2. And so what does that mean kind of like in 2D, right? So in 2D, it's like saying, okay, I have a bunch of, points from one class, and I have a bunch of points from another class, black X's and red O's. And then I have a straight line like this, and the equation of this line is W transpose X plus W0. And basically everything on one side of the line gets called class 1, and everything on the other side of the line gets called class 2. So in higher dimensions, this is more like, imagine that we're trying to just draw a discriminant inside this room, right? So what I might do is imagine a giant plane that swipes through the middle of the room and separates all the people on one side of the plane and all the people on the other side of the plane. That's a way I can use a linear function to split this room into two, okay? And of course, life is good in this situation where the classes are what are called linearly separable, right? So in this picture, the data is what's called linearly separable. Separable is an A, right? Yeah. Right? That basically means that there is an ideal line that, given the data, completely isolates one class from the other, right? Now, in the real world, it may be that the classes are mixed up a little bit, in which case there is no single line that will do it all, and we're in the position of trying to find the best line in some sense, okay? And so in some sense, what we're going to talk about today, the next lecture, and the one after that, are different ways of drawing that line, right? Even in this case, where the classes are linearly separable, you might ask yourself, what would be a good criterion for drawing the best line, right? So I mean, there are an infinite number of lines that could work, and kind of the argument is, well, like this line would also work, but somehow it's less satisfying than the other line, right? So maybe it's skating a little bit too close to the one black set of x's, right? So we'll talk about that in a couple of lectures, right? Kind of like, what are some criteria for drawing that line? But in general, what we're doing is drawing what's called a hyperplane, right? So let me just say that in general, right, in higher dimensions, we are finding a hyperplane that separates the data into two pieces. And so a hyperplane is nothing more than an entity that is one dimension less than the space where the data lives, right? So if you guys are all like 3D data points in the world, then I have a 2D plane that separates into two halves. If I just have a set of points on a line, then I have like one position, which is like a kind of a single point, right? If I have points in a plane, then I have a line, right? So it's kind of like one dimension down from the data space is what a hyperplane means. And again, just like in the case we talked about before, often we basically augment the data, like, we basically take the ith data point and we take, what we had and we put a 1 on the end of it. So we just use, y equals w transpose x, right? That's like saying that we kind of incorporate the bias into the weight vector. And the last element of the weight vector is the thing that's actually the constant term. Okay, so we're going to talk about both two-class classification, right? Dogs and cats, or we're going to talk about multi-class classification, right? Classification into, what major you're in, right? And so I want to first kind of talk about why it's not as straightforward as you may think to do the multi-class problem, right? So kind of like, how would we approach the world of multi-class classification if I was kind of drawing straight lines across the data space, right? So let me just say that, how should we approach K-class, classification when this K is, greater than just 2? Well, there are a couple of ways you can do it, right? So the first way is called, one versus the rest. That's basically like saying, I'm going to say if I have K classes, I'm going to, I have K classifiers like, class K versus not class K. So, for example, let's suppose I have, a bunch of points over here in class 1. I have a bunch of points over here in class 2, and I have a whole bunch of points over here in class 3, okay? So what I could do is I could say, okay, I'm going to draw one line that says, so if I call this class 1, if I call this class 2, and I call this class 3, if I'm going to do this with just straight lines, I could say, well, here's a line that is basically either 1 on this side or not 1 on that side, right? Does a great job of classifying the data, right? And then I could have a classifier that looks like this, which is kind of like saying, 2 on this side and not 2 on that side, right? Okay, so I guess the question is then, what happens when I have something that is like over here, right? This is not so great because there are some points that are like both 1 and 2, right? So kind of this is, maybe not the best because, I'm sorry, 1 and 2 is like, wait, it's got to be this side and it's got to be on this. Maybe I should draw another picture like this. This is like, 3 on this side and not 3 on this side. So there's got to be some confusion here, right? So for example, let's find a bad place. Yeah, so like everything over here is, kind of both, both 2 and 3 according to what these classifiers are telling me, right? So somehow kind of taking the votes of all of these classifiers is not like so straightforward, right? I need more than that, right? Another way I can do it is to say, okay, I'm going to look at every possible set of class-to-class decision boundaries, right? So I could say, or I could have another way of doing this, which is like kind of 1 versus 1. That's like saying all possibilities of class I versus class J binary classifiers, right? So they're going to be, if I have k total classes, I have this many, lines or hyperplanes in space, right? And then what I could do is, classify according to majority vote. So again, let's kind of draw this picture again. So I got, class 1 over here. I have class 2 over here. And I have class 3 over here. So I guess I actually need to have more classes to make this look that different from the one I drew before. But let's suppose I have kind of like the, 1 versus 2. It's okay then for these lines maybe go through this, right? So maybe this is like the, 1 versus 2. And then maybe I have, 3 versus 1, like this. And then maybe I have like, what do we have left? 2 versus 3. So if I have a point like over here, I might say, okay, well, what is this voting for? So it's on this side of the 2 versus 3 line, and it's on this side of the 2 versus 1 line. So majority vote would say that anything in here should be classified as 2, right? So that seems to work okay, but what about like over here, right? So there's a big like weirdo zone in the middle where here, this classifier is voting for 2, this classifier is voting for 1, this classifier is voting for 3, right? So it's like, how do I break that tie? What do I do in the middle, right? So neither of these things is exactly the most, exciting answer, right? The right way to do it is based on this idea of linear discriminants, where we're going to have basically k linear functions and take the one that's the maximum, right? So these 1 and 2 are kind of like, definitely will work, but there are always these weird corner cases where you're going to come up with ambiguous or undefined classification situations, right? So the right way to do it is the following. So kind of the right way is basically to build k linear functions basically one for each class. So I have a weight vector and I have a bias for each class. And then the discriminant function is the following. I basically assign a point to class K if its discriminant value is bigger than all the other ones. So this results in decision boundaries in the space that kind of divide up the world into a set of straight lines, right? So again, if I have kind of like my class 1, class 2, class 3 situation, then the result of doing this is going to turn out to look something like this, where I have, the plane split up into regions where it's kind of clear that each point goes to only one of the classes. Okay, so here, this results in decision boundaries are, basically straight lines, or more generally, they're hyperplanes. And another nice thing about this is that the decision regions, right, the set of points that are assigned to each class are convex, right? Meaning that if I draw a straight line between any 2 points in the region, it stays in the region. So the decision regions are convex. So that's nice. Okay, so kind of the name of the game is going to be designing a good YK for this, for the two-class problem and for the multi-class problem. Okay, so let's talk about how we actually estimate those parameters. Okay, so one kind of natural way to think about it, but probably not the smartest way to do it, is to kind of apply our regression techniques from last time to this problem, right? So how to estimate the best parameters well, kind of, not great way, not great, Bob, is to use kind of like the standard tools for regression, like use least squares regression. Meaning that I could try to minimize the sum of the squares of target values minus linear functions, where this t is equal to some one-hot encoding of the class. What do I mean by that, right? So, that's like saying that, if I have a function, or if I have a observation that is in class 2 out of 5 classes, then my function t would be like saying, okay, I want to predict this target, right? So this is like saying, class 2 of 5. And then what I could try to do, is I could try to take all of my observations, I could try to regress them against these binary vectors, and then I could, for a new class or for a new observation, I could get a bunch of numbers for the observation y and just take which one is bigger and call that my class, right? So that is, doable, but not great. And one of the reasons it's not great is because of the problem that we talked about at the end of last lecture, which is that linear regression, we know, is very sensitive to outliers, right? So that's one problem, is that a few points can throw this line way off, right? So let me just say that, first of all, how do I do this, right? So we could learn W and then choose you know, the maximum index of W transpose X for some new observation. So again, why is this not like the best answer? Well, the main thing that I want to say is not good is, you know, it's sensitive to outliers. Bless you. Right? So if I had, you know, just say two classes, like class 1 and class 2, maybe I would do my, you know, regression and I would get this boundary and life would be okay, right? But then let's suppose that I, you know, added some more points like over here. Kind of what we saw in the demo from last time was that that would probably shift the boundary over to be, well, not through the line, but something more like this, right? And we don't want there to be such sensitivity to these outlying points. I mean, the original black line would have already done a fine job of classifying the two classes. I don't need to move it, but these other points will force that line to move just because of the way that least squares works. So, you know, the main idea is that, you know, distant points have a oversized effect on where the line is. The other thing that it turns out, just kind of like the way that these things work out, is that, you know, suppose I had some situation like this, where, you know, if I had a bunch of points over here and a bunch of points over here and a bunch of points, where's my blue pen, over here. What can happen with trying to do it with regression is that you may get some sort of a situation where your, you know, boundaries look like this, right? Even though there's a great linear discriminant, right? There is a linear discriminant that basically will, if I draw just like two lines like this, will ideally separate the data, right? Linear regression is not going to find that. It's going to do something that's more like this. So the result of this is, you know, lots of misclassified points, even though, you know, ideal separation is possible with lines. And again, the reason, question?
So that second one is the linear, that's not the least squares?
I mean, this is the same kind of least squares, linear regression, kind of the same thing, right? So basically what we talked about last time was solving this kind of like least squares problem, trying to minimize the difference between the target vector and the model, right? So that's kind of what happens if we try to do that here. And the reason that this happens, right, why do we get this weird bad behavior? Well, the problem is that, again, remember what our model was for the way that the observations were related, right? So why does this happen? Remember that the regression model is that the, you know, observation equals truth plus noise, right? And this noise is like Gaussian. And our kind of assumption is that the observations that we see are close to our model plus a little bit of fuzzy noise, right? But the problem is that, you know, this doesn't really work for binary observations or one-hot vectors. Right? If I tell you the class is, you know, if I tell you the y is 0, 1, 0, 0, 0, it's not like that is some sort of underlying, you know, thing that's like some real vector that has non-binary values that's kind of noised up to get to that binary thing. The model is totally different, right? So, you know, when I'm quantizing into classes, this Gaussian noise assumption is not really the right one to use, right? So, we want an error function that is more, directly designed for classification. And kind of that's what we're going to be talking about for the rest of this lecture and for the next 2 lectures, right? So the first approach to this problem that I want to talk about is kind of a simple and clever idea called Fisher's discriminant, Fisher's linear discriminant. So, this is a clever idea that makes a lot of sense. So Fisher's linear discriminant. So kind of the idea is that I want to find a one-dimensional projection of all the data that separates the data as much as possible. And this is much easier to illustrate than it is to say, but let me just write it down. So the goal is to find a 1D projection that separates the classes as much as possible. And I'm going to quantify what I mean by that mathematically in just a moment. So let me just kind of illustrate this with a picture. So here's my little demo. Right, so suppose these are my classes, blue and red, okay? And suppose my idea was, okay, I'm going to just project those points down onto the x-axis, and I'm going to decide on a threshold that says everything on one side of the threshold is blue, everything on the other side of the threshold is red, right? If I look at this picture, I can see that this is not a great way to do it because the blue classes and the red classes, when I push them down onto the x-axis, have some significant overlap, right? Now, it does seem clear, though, that if I were to rotate my frame of reference, maybe I could find a way so when I push these guys down, they are well separated, right? So what I can start to do is like rotate this around a little bit. I can say, okay, what if I rotate this guy by 20 degrees? It's the same data. Actually, now I'm making it worse, right? So actually, you can see that if I rotated this even more, this would be the worst possible idea, right? Where I take the data, now it's almost indistinguishable, right? So what I should be doing is rotating it the other way, where now I can see that there is definitely a line that clearly separates the blue and the red classes, right? So that's kind of the philosophy here. So what I'm trying to do is I'm trying to find a way to push the data down onto one axis in such a way that that number one, the classes are well separated, and number two, that the classes are nice and tight in their own cluster, right? And we know that if I was to measure the error rate, it would be related to, if I draw the line, it'd be kind of related to how much PDF energy is there below the tail on each side. So if we talked about this in the Bayesian decision theory world, we would talk about the error rate being the integral of the red PDF on the left side of the line plus the integral of the blue PDF on the right side of the line. Now, life is not always so great when you have data that is not ideally separable, right? So here's another example where, again, red points and blue points, if I push them down, I see this. Well, I can rotate this around all I like. If I try again rotating it off to the left a little bit, it's maybe a little bit better, but you can kind of convince yourself that there's no place I can turn this data that is going to result in these distributions not overlapping at all, right? So what I have to do is just do the best I can, right? And that's what I'm going to mathematically pose for you now is what is the nature of kind of doing the best that you can. I want to have very little overlap between the distributions if possible and push them as far apart as I can and get them to be nicely well clustered, okay? So kind of mathematically what I'm doing here is I am choosing a single scalar to represent each higher dimensional data point, right? So this is just showing you going from 2D to 1D. In higher dimensional data, like if I have 10-dimensional data, I'm still trying to find the best one-dimensional projection down onto some line, right? And so let's talk about that process. Okay, so, and again, let me just kind of sketch this for my notes. just to kind of show you what I drew in MATLAB. So again, if I have class 1 and class 2, if I push them down onto this line, then there is kind of like significant overlap between the classes, right? So what I might do in this case is say, okay, everything on this side of the line is class 1, everything on this side of the line is class 2. That's going to result in a lot of mistakes, right? Whereas if I were to instead take the same data and, really, it was easier for me to rotate the data in my MATLAB example than it was for me to rotate the line. In this case, I can draw it more easily by saying, okay, what about this line, right? If I project things onto this line, then from this axis, things are like here, and this axis, things are like here. Then I would draw my decision line like this, and that would be clearly a much better decision rule for classification than what I did before. Okay, so let's talk about how to kind of formalize this in a mathematical way. Let me stop and ask, is everyone clear on the kind of basic idea? Okay, so let's just say what I'm doing. So mathematically, this is like creating a scalar value out of my vector input via this equation, W transpose X, right? So X before was a vector. After I do this, I just get a number, right? And then we threshold on Y to do the classification. Okay, so let's do this for two classes first, because that's a much easier way of doing it. So for two classes, and again, you're going to see this called binary classification, which is a good general term to know. It's always easier to talk about things as binary classification problems first, and then kind of generalize to the multiple class situation. So what I'm going to do is I'm going to say, okay, suppose that I have, drawn this best line, right? So I'm going to say that, let's say that we let, draw the line, separate into classes, right? So I have a candidate line. I'm trying to find the best one, right? So that means that I can create the mean vector of saying these are all of the points that were assigned to class 1, right? And then these are all the points that were assigned to class 2, and I can figure out what the means of those things are. Actually, this is very much like the means that we did in k-means clustering, right? Same idea. We just decide what are the class means, okay? And then we can also project those means onto the vector. So again, this is like saying, here these are the means in observation space, and here these are the means in 1D space. So basically, these are like, projected class means in just 1D. Okay, and now I can kind of say, okay, I want to measure both how tight are the classes after I do this classification, like how tight are those clusters, and then what is the kind of relationship between the two clusters, class 1 and class 2. So there's something called the within class variance and the between class variance. So let's define what those things mean. So the within class variance after I project is what's called this, sk squared. So I basically have two of these. I have k equals 1 and 2. And I have the set of points that are inside class K. And I'm going to look at, the projection minus the center. Right? This is basically like saying, what is the variance of the points after I project them down onto that, line. So that's basically saying, okay, I have all the points. I, project them down onto this line. Now I have a bunch of measurements here. My CK, my C1 is the point in the middle, and then this number S1 squared is basically the variance of the points along that axis, right? So I do this for both of the classes, and then I compute, the total within class variance as just the sum of these numbers. So I want these numbers to be small, right? Ideally, I want the projections to be like as low variance as possible, right? It would be great to have just spikes that were, very little, deviation from the mean. That would be the best case scenario, right? On the other hand, I have what's called the between class variance. So the between class variance is basically saying, what is the square distance between the cluster centers, right? So after I push these guys down, here's class 1, here's class 2, I want to know how far apart these numbers are. And so I want that number to be big, right? I want to try to push these guys as far apart as possible after I projected them down, right? So the idea is I want this to be big, and I want this to be small, right? And so that makes kind of sense that we're going to build a cost function that is exactly like that, right? So it's going to relate these two things. So let me just write down, we want this to be small, and we want this to be big, right? And so what I'm going to do is I'm going to take the ratio of these things. Right? I'm going to put the between class variance in the numerator, and I'm going to put the within the class variance in the denominator, and then I'm going to hopefully get a big number, right? So my objective function is as a function of the weight that I choose, it's basically, the between class variance over the within class variance, right? This is like the between class over the within class. And what I want to do is maximize this. And so now I need to be a little bit more explicit about how are these C and S values actually computed from the data, right? So here, this is a function of W, but W is not actually very obviously in this equation, right? So let me write that down. It turns out that this J of W can be written as follows. W transpose times one matrix up here, W transpose times a matrix down here. Maybe I should kind of make sure it's a subscript. So here, this between class matrix is given by this thing. And this within class matrix is given by this equation. So it kind of makes sense. All I'm doing is I'm actually writing down, what is the variance of the points in the original feature space, and I'm building those covariance matrices, right? So I've told you that these are the means in the original observation space, right? So this is basically like the square of that thing. And then this is, I sum up over each of the classes, what is the observed variance, basically, right? So now I basically have something that has got, a little bit more explicit, function of W. Here, I guess I still haven't actually, said where the W's come from. Well, W's are kind of coming in via the, assignment of the classes, right? So I can show that to minimize the function of this as a function of W, right? So here, I guess the W's are here, right? So here, these are where the W's are. Well, I could point to them, W, W. So these matrices don't depend on W. These things do depend on W. And this is, again, like a take a derivative and set it equals 0 kind of situation. And I'll just tell you what the answer is. So if I, differentiate, this with respect to W and set it equal to 0, it turns out that the answer is this. It's the within class matrix like so. So this is the bottom line, okay? Which you could derive yourself by taking the derivative and set equal to 0, but I did it for you, okay? So it's pretty straightforward, right? It just means that I can compute these things and then I'm done, right? So these things only depend on, the means, right? So make sure I'm doing this the right way. Well, okay, so I realize that I need to be clear that there are the original class labels, right? So I'm giving you class 1 and class 2. So I already know, basically, these things, these come from original ground truth class labels, right? So all this stuff actually is coming from the original ground truth class labels. So I already know which points are black and which points are red, right? Okay. And so when I do this, I end up with a W star, which is like my best hyperplane equation. So this gives the normal direction to the discriminating hyperplane. More explicitly, the dividing line is perpendicular to W, right? So like if you guys have ever done computer graphics, you know about the normal to an object, right? So it's kind of the same thing here. So if I have a plane, what I'm doing here is I'm getting a vector. This vector is W, and the dividing hyperplane is basically perpendicular to that vector, like this. So this is like a one-stop derivation for the best parameters I can get, okay? And so let's take a look at some examples, okay? So let me just go back to my thing here. So if I look at, so here, this is the other Fisher demo. This is actually multiple classes. Well, okay, so let me just say before I go back to this, is that this is like what I do in 2 classes, right? So in general, you can do this in multiple classes, right? So it's just a little bit harder to write all the math. So the way that this guy Fisher originally formulated the idea was with the two classes, and it's very easy to understand the between class and the within class variance and write it down like this. However, when I have multiple classes, life is more complicated, right? So I can't write it down for you so easily. I can tell you that this can be generalized to the K-class solution. And you can see Bishop for the details, right? If you want the Gorey equations for the K-class setup, then it's in the book. In general, this kind of process is called LDA, or linear discriminant analysis. So if you're looking in, a library for, not a book library, but a code library for like Fisher's stuff, probably what you're going to come up instead with is linear discriminant analysis, or LDA. And then if you read the help files for LDA, it'll say uses Fisher's criterion for separating the classes, basically. So what else do I want to say about this? So let me just say that this is going to tie into something that we're going to talk about after the first exam, which is, it's kind of like what you would call a dimensionality reduction of the data, right? So we can think about this like a type of dimensionality reduction, which we're going to talk about more later. So if you've ever heard of something called principal component analysis, for example, it's another type of dimensionality reduction we'll spend a whole lecture on. But kind of what I'm doing here is I'm taking 10-dimensional space and I'm reducing it down to 1 dimension, right? So that's one thing. The other thing is that there is definitely a relationship to the Bayesian decision analysis we talked about before, right? So the other thing I want to say is that if classes are actually Gaussian, and I basically have like within class covariance matrices are isotropic. What that means is that the sigmas that I have are equal to basically just like circular probability contours, like the identity matrix. Then that's kind of like the world where I have, the points are roughly scattered in a, circular way, right? So if I had, this was my class 1, and this was my class 2, one kind of nice thing about the situation, which is pretty obvious from looking at it, is that if I draw a line connecting the cluster centers, and I basically draw this perpendicular line here, it seems pretty clear that the dividing line that I should choose is basically perpendicular to the line connecting the means, right? So this is the line perpendicular to, or maybe I should say, this is the hyperplane perpendicular to the line connecting the means. It's kind of like saying that when I have that kind of setup, the best I can do is to orient things so I'm projecting down onto that line, right? It's not true in the general case when the matrices are not round, right? So if I had something like this, if I had like, here's class 1 is kind of more elliptical, and here's class 2 is kind of more elliptical. Well, again, it's pretty clear that the dividing line like this would be good, but that line is not, perpendicular to the line connecting the means, right? So for this to be true, you have to have these kind of isotropic circular covariance matrices. Okay. So let me just show you some examples of the linear discriminant analysis you can do, kind of generalizing it to multiple classes. Let's actually look at some data, right? So here's an example of, this is actually a case, I guess it's the same Fisher. There's this data set that he gathered from flowers, irises. So if you look in MATLAB, there's this Fisher iris data set, and you can choose some vectors of this data set that correspond to the length and the height of petals and stuff like that for a certain classification. So here's a case where, again, I've got 3 classes, and I've drawn these linear decision boundaries, and it does pretty well, right? This is a case where there aren't, certainly the black class is easy to separate, and the red and the blue classes have a little bit of entanglement, right? If I have a slightly more complicated situation, like here's another case where, we've got kind of like this V shape where there's definitely more, contamination between the red and the blue. But here you can kind of see the way that these linear decision boundaries are forming this kind of convex, separation of the plane, which is kind of nice. And so here, this is just another example of what you get. And then here's an example where things don't work out so well, right? So I've got, black points on the left and the right, red points at the top and blue points at the bottom, right? And kind of the best I can do is more or less classify everything as black, right? Because if I'm only allowed to draw a single straight line per, if I'm only allowed to draw 2 straight lines in this world, then I'm going to have a hard time deciding these trickier cases. So that kind of raises the question about, well, what can I do in situations like this, right? Well, one thing that we talked about in the regression lecture was that what makes linear regression. What makes it linear is that it's linear in the W parameters, right? So, we can, we can get decision boundaries that aren't straight lines by using, nonlinear functions of the inputs, right? So basically, my y then becomes, W transpose phi of x, where this phi of x is possibly some sort of a feature vector that I derive from x. And I can still use the same equations to find the best W, but I'm doing it in a feature space that is not the original observations, right? So for example, what I could do is what's called, quadratic discriminant analysis. Which is like saying my phi, say I'm doing this in 2D, right? So if I had, x1, x2 in the plane, I could make a function that is basically, if all I had was this, and I was looking at W transpose times this, that would just be the same hyperplane I had before. But now if I add in some more quadratic terms and mixed terms like this, so now I'm basically allowing myself to build a function of, terms up to x squared, right? That means my decision boundaries are going to look generally like, not straight lines, but more like parabolas, right? And so if I apply the very same approach using the same kind of, discriminant analysis, what I can get is something like this. So let me go back to my illustration for a second. So here's my original situation, if I say, okay, you're allowed now to look at a quadratic discriminant, well, my decision boundaries now can look very different, right? So here, you can kind of see that this red region is now kind of like this tongue in the middle of the image where the boundary is like a parabola shape as opposed to a straight line, right? And all I did was I changed the features to be nonlinear, right? So that's something that, again, it's the very same kind of, equations, but with different basis functions, different phis, right? If you remember last time, we had this phi matrix that we used in the regression. It's the very same idea here. And if I apply this to my other data sets, for example, if I apply it to the one where the black points were on both sides and the red points were at the top, blue points at the bottom, I can get much better, classification like this, right? Still not perfect. I mean, there's some inevitable problems because of the way that the points are all kind of mushed together in the middle, but I've done a much better job of kind of getting these parentheses of the black points that I'm saying, okay, all you guys are on one side. So in some sense, this is a much different way of doing classification, okay? And the key idea in general for a lot of machine learning is that adding some nonlinearity can help you, right? So that's going to definitely be a theme going forward, is that, if we additionally add what's called an activation function, a nonlinear activation function, and our model is like some function times some weights times some features. So here, these are basically, my features. This is some nonlinear function. So this is the fundamental building block of what we're going to talk about in the next lecture, and we're going to talk about with neural networks, right? So this is basically the basic concept for, what we're going to talk about next time, which is called logistic regression. And more generally, neural networks. And the first one we're going to talk about in that world is something called the perceptron. Perceptron. So that's going to be something we talk about after the first exam, okay? And so that's kind of where we're going. The other thing I'm going to say is that to look forward 2 lectures from now is changing our cost function for what we mean by a good classifier, right? So also, this is kind of like one thing, by changing our cost function for what makes a good classifier, we can get what's called, something called the support vector machine. Another futuristic sounding object, SVM. So you may have heard of SVMs for classification. So we're going to talk about logistic regression next time and SVMs the time after that. These are all basically different ways of changing our model for what makes a good classifier and arriving at different decision boundaries. And so that's kind of where we're going. All right, let me pause and ask. Any questions or comments? Yes?
In the previous page, concerning, so I'm sort of used on the idea behind the quadratic discriminant analysis, kind of like how that, I get the fact that adding nonlinearity makes the application more accurate, but kind of like I'm confused on like I guess like how the math backs up the result, if that makes sense.
So let's just talk about this in a little more detail. So suppose this is my function, right? So that would mean that my W transpose phi would look like, something plus constant terms times x and y plus, a new constant term times this thing plus this thing plus this thing, right? So that's going to be my new y of x, right? And if I think about just in 2 dimensions, for example, plotting that function in the plane, it's going to look like a, parabola, right? If all I had was this, all this function could do would be look like a straight line, right? So this is allowing me to curve my decision boundary around in a more complicated way, right? So I can only do better by allowing myself these extra degrees of freedom, right? Because in theory, this thing can do everything that this does if I just set these numbers equal to 0, but it gives me additional freedom to make the decision boundary better, right? If that kind of makes sense.
Yeah, where is the y component?
Oh, I guess here I guess that this was my x2, right? So this is like saying that I have points in the plane, right? This is my x1, x2 axis, right? And so these are my points over here in class 1. These are my points over here in class 2. So say, for example, that I had class 2 kind of wrapping around class 1 in this way. That would mean that I could hopefully draw a decision boundary that would look like this, right? That would be impossible to do with a single line. So again, it comes down to, like I said, in the easiest case, our classification problem is what's called linearly separable, meaning I can draw a straight line between them. It may not be linearly separable, but maybe it's quadratically separable, right? And of course, if I were giving myself the ultimate degrees of freedom, right, I could imagine drawing some sort of like a, even in this case over here, I could imagine drawing some sort of like crazy classification boundary that just like literally carved out every blue triangle and every red triangle and kind of like had 100% classification of this data, but then it's like not a very generalizable model, right? So it's not a very low parameter model. So that's kind of, again, the constant trade-off we have is how simple is our model versus how well does it potentially classify, right? And so the other thing is that, it's a pain to try to, not a huge pain, but, it can be a hard time deciding, okay, what would be some features that would be a low dimensional set of features that would do a good job of separating things in space. In some way, that's what the next phase of machine learning that you're going to learn about is instead of handcrafting the features, we're going to just learn the features by letting this neural network kind of learn what good features should be for the data, right? So that's going to be the kind of cool thing is it will take the heat off of us in terms of having to decide, okay, should I use a secondary polynomial or a third degree polynomial? Instead, we're just going to like let the neural network kind of figure out what the right basis functions are and then do the best job in that new space. Okay, other questions or comments? All right, so let me stop the recording for today.